Okay, so here I'm going to explain the zero order integrated rate law. So integrated rate laws account for the time in the reaction. So we follow the concentration versus the time. Remember, for zero order rate law, the differential rate law or rate law, if we're looking at some generic equation, just A, zero order means this is raised to the zero order. Anything raised to the zero order just equals 1, so the rate is just equal to k. And so if we want to look at how this is integrated with time, just plot a graph here of concentration versus time. Now, usually these reactants decay exponentially. There's a curve in here. Well, if you look at the rate law, the rate of decay or the rate of dissociation or reaction is just equal to a constant. That means at every time interval, you're losing the same amount. That's constant. So if you plot the concentration of reactant versus time, you're going to see a straight line with a negative slope. In other words, the line is going straight down. So the integrated rate law is simply just your linear equation. Y equals mx plus b. So Y is your concentration of A. M is the slope. Well, this is a straight line, so the slope is K, but be careful. The slope is negative. So you have to put that negative sign in there. X is T. B is your y-intercept. The line crosses the y-axis at the initial concentration of A. So this is the equation for zero order integrated rate law. Now, let's just talk a little bit of what this looks like and what's going on here. What we're saying is, if we know the initial concentration and we know the rate constant, we can always plug in a time, 5 seconds, 10 minutes, 30 hours. We can always plug in a time and calculate what the new concentration is going to be. The half-life. The half-life, by definition, is the time required for the initial concentration to be cut in half. And we'll call this T 1/2. Now, this equation is always given to you. Initial concentration over 2K. K is the rate constant. So in other words, how long does it take for the reaction to be cut in half? Plug in your initial concentration divided by 2 divided by the rate constant, and that's how long it will take. So this is always going to be given to you, but let me give you just a brief explanation of how we get there. If we look at the integrated rate law, and remember, half-life means we want to know the time it takes for this number to go to 1/2 of this number. This is the initial concentration. When the initial concentration gets cut in half, what's the time? So look at what I'm going to do here. I'm just going to substitute the A naught over half, or I'm sorry, A naught over 2 for A, minus KT plus the initial concentration. If I subtract the initial concentration from both sides, so of course this cancels. This is initial concentration over 2. This is initial concentration. So this is kind of like a, just to look at the fractions here, this is a 2 over 2. That's the same thing as 1. And so pretty simple here. 1/2 minus 2 over 2, well, this just becomes negative 1/2. Is equal to negative kt. How do we get t by itself? Divide both sides by negative k. And of course, you see the negative signs cancel, the k's cancel. And so the time that it takes for the initial concentration to be cut in half is equal to A naught over 2k, which is our half-life. So this is the summary for the zero-order integrated rate law. This is the zero-order integrated rate law. It allows us to calculate the concentration at any time as long as we know the rate constant and the initial concentration. If we ever want to calculate a half-life, we can use this equation. Or if the half-life is given to us, we can always rearrange this to solve for the rate constant.